Alright, welcome to another video here in our Module 6 videos, and this one here is the second video in terms of this dot point here, which is looking at the actual formula. In the last video we looked at this idea that charged particles in uniform magnetic fields can undergo acceleration, and when they undergo acceleration they produce their own magnetic field. They also have a relationship here in terms of the perpendicular to the field, and we did actually cheat a little bit and we did look at this equation and did some mathematics. Can't help it, but that's what we did in the last video. But in this video we're going to be focusing more on this equation, revising some of the concepts and adding a bit more information. That's how you learn. Remember, you constantly add a little bit more of information and revise what you've previously done and make sense of it. Now, of course, this video here, like all the videos in Module 6, are free on YouTube for this whole course. And if you like this video, of course, you can come over to the schoolhomeworklab.com and join the whole HSC Physics course, where you'll get, of course, all the modules and lots of other advantages, which I'll tell you at the end of the video. But let's get into this concept now. And of course, if you like it, don't forget to like, subscribe. It's going to help the channel out, helps me make more videos and to keep your brain cells pumping and to get you the maximum marks possible. So let's look at this relationship of this formula here. Now, we know from the previous video that when we have a charged particle and it enters a magnetic field, it undergoes circular motion. And we looked at that concept previously, but we're going to make sure we reinforce it. You can see with this diagram here, what I've tried to do, and I'll just enlarge this diagram for you, that you can see when this particle goes into the field, it experiences a force going inwards, and that is at 90 degrees to its motion. And so that is FC, the centripetal force, and of course that's equal to the magnetic force there. And so particles that enter a magnetic field undergo circular motion. And of course you can see the video playing below of the Aurora Borealis, and that is one application of charged particles interacting with the magnetic field. With the Aurora Borealis, if you remember from the last video, we said that when a particle enters a field at not 90 degrees, it can undergo circular motion. Well, with the Aurora Borealis, that's the sort of what's going on there. Charged particles from the sun interact with the magnetosphere of the Earth, and of course they then interact with oxygen atoms and other gaseous atoms to create this phenomenon, which is absolutely beautiful. And we can see that we've got a picture there showing you that when you have these charged particles from the solar wind, they get funneled down to the poles, and then we have the Aurora Borealis, and then have the Southern Australis down there as well. So that's all this interaction of charged particles. Well, let's have a look at this equation. It's a little bit more detail here. We did touch on it in the last video. Couldn't help myself, had to do it. But we can see that when a charged particle enters a field, it feels a force, and that force is known as FB, the magnetic force that it feels. And we said that the magnitude of that force was based on the size of the charge, the velocity of the particle, the strength of the magnetic field, and of course the angle at which that particle enters the field. Now, the way I've drawn this here, it's entering at 90 degrees. And so sine of 90 is 1, and so really that just cancels out there when we times it by 1. But we can see the effect, what's going on here. Now, here's a sample calculation, a simple calculation. It says a magnetic field is set up as shown above. A proton is fired into the field at 90 degrees, and it is at 40 meters per second. Calculate the force of the proton experiences when it enters the field. Now, of course, when you do this, and we do our HSC questions, I always recommend that you highlight the key ideas, because when you do it in the HSC, remember, an exam technique is you've got to narrow down what part of the syllabus is the question testing. So by highlighting the key terms, that's going to allow you to filter out and go, oh, this is actually testing this formula, right? So that's what I would tend to do. So you go magnetic field, okay, it's important there. Then we go, okay, a proton is fired into the field. I'm going to change the color here because that's a bit too dark. And you go, okay, it's 90 degrees, and then straight away your eyeball will go, okay, so that means sine of 90 is 1, so we can cancel that out of the equation. And this is the thinking that you're going through here, so let's just change that color again. And then we go, okay, it has a velocity of 40 meters, and what have we got to do? We've got to calculate the force. So straight away you would be thinking about this equation here, and you would start writing out your variables. And so we've got our proton, it says, So then you go to the back of the data sheet and you get the charge, okay? And it's just the opposite of the charge on the electron. We know the velocity, we know the angle, and we know the magnetic field strength because it's given. So now we look at our equation, we write it down, and we go, okay, the only thing we don't know, of course, is the magnetic field, so the force on the charge. So we put everything in, and that tells us the magnitude. Now, that's only half the question because we've got to talk in terms of its direction. Remember, force is a vector, and so it needs a magnitude plus direction. So this is where we use our right-hand palm rule, and then we work out the direction. And so remember, with the right-hand palm rule, our thumb, I should say, goes in the direction of the particle. So we've got like that. Fingers go in the direction of the field where there crosses here, so we put our fingers into the page. So get your right hand and practice right now. And when you do that, you're going to find that the force comes out of your palm, which is telling you it's going upwards. And so just like the diagram here, it's saying that we have a force going upwards. And so therefore we say up the page. Okay, and in HSC questions, they will have a variety of different answers, right? They will have this answer here saying up the page. They'll have another one saying the same numerical value, but down the page. So they're testing not only can you calculate the answer, but can you determine the direction using your right-hand palm rule. So make sure you don't forget that. All right, so here is another one here, and this question here is a little bit different. So let's read it out and see. It says a particle of mass m, whoops, that's not the highlighter, so let's get rid of that and let's switch to the highlighter. A particle of mass m and charge q, right, enters the magnetic field shown traveling at velocity v. If another particle enters another field twice as strong, so 2b now, with half the velocity, what would the mass need to be in order to maintain the same radius? Okay, so they're just testing your ability here to see how changing one variable or two variables affects the magnitude of the force. And this is the equation here, right? And so it's saying about the radius. And so to work out the effect of radius, we need to derive an equation for that. And then we need to see what the effects of changing those variables are. And so we did this in a previous video, but let's do it again. We know that when the force goes into the field, when the particle goes into the field, it's going to experience a force. Now remember that that force is 90 degrees to the direction of motion. That's going to cause the particle to undergo circular motion, right? So its tangential velocity is going that way, but then we have some force acting on it, and so that's going to change the direction of motion. And it's going to undergo circular motion. So since we have this relationship here, we can then make, we know it's going at 90 degrees, so our sine theta goes to 1. So there's our QVB. We make that equal to the net force, which is our centripetal force. And then we do some algebra, rearrange to make mass the subject here, because it says what would the mass need to be to maintain the same radius. And so what we've got to do is we've got our formula here, and now we just change some variables. It said in the question here that if another particle enters the field with twice the field strength, 2b, when we do this, just make everything equal to 1 and then multiply it or divide by the factor they tell you. So we've got b, so if it's 2b, it's just going to be 2 times 1, which is 2, so you can see I've got a 2 there. I've made the mass, the radius the same, I've made the charge the same by just putting 1 in. And it says half the velocity. So my velocity down the bottom, instead of putting 1, I now put 0.5. And when I do that, it says the mass needs to be 4 times as greater. Okay, so therefore the mass would need to be 4m. Whatever the original mass is, the new mass will have to be 4 times that original mass. So the answer is 4m. Okay, so that's just a different type of question where they're testing you on a variety of things here. They're testing you, can you use this equation? They're testing you, do you know that it undergoes circular motion? Can you rearrange that formula to make mass the subject? And then they're giving you some ratios or some changes in variables to see how that would affect the particle. And so we've done that down there by putting in 1 for everything, and then we just multiply it or divide by whatever the factor is in the equation, in the question I should say. So that's a different type of question there. All right, let's have a look at some relationships here, which is sort of what we have done previously in the last video a little bit. when we used our simulator. Well, here, if we look at our particles going into the field, this is now looking at ratio and formula manipulations. So trajectories of particles once they go into the field, as we know, are circular motion. But how do they change? Well, we derived this equation in the last video, and we sort of showed you a bit how to do that in the last slide. But let's do it again, right? Let's test your brain cells. To get this ratio here, what did we do? Well, we had to make FB is equal to FC, and FB was QVB, and FC was mv squared on r. Then we make r the subject, so that velocity there will cancel out with one of the velocities, and then we bring r over here, and we divide by QV, which means that we have mv divided by QB. So that is our relationship we've got there. Now, what are the relationships between each variable? Well, the radius is directly proportional to m. Okay, if we make everything else, the velocity, this 1, and the magnetic field strength 1, then the radius is proportional to m. And we can see that the radius is proportional to m, right? Directly proportional relationship. And if you remember from the last video, when we used the simulator, we actually found that. Remember, when using that simulator, we increased the mass of the particle, and we saw that the radius increased as well. What's the relationship? Let's rub out some of these. What's the relationship between radius and magnetic field strength? Well, it's inversely proportional, isn't it? So here we have r, and b is on the bottom, so r is inversely proportional to b. And we saw that happen as well. When we changed the magnetic field strength, we saw the radius change in the inverse direction. And so all I'm doing here is I'm just using my relationship to construct some graphs here. This is very, very important skill because they test you all the time with our formulas in the data sheet, specifically in multiple choice questions, and they get you to work out which graph it is. So I encourage you to do that with every single formula. And remember, with our formula sheets, you should be drawing these ones down here. So that's another way in which they can test you, is formula manipulations. Alright, so that's it for this video here. We looked at the formula in a little bit more detail here, so a little bit of active recall. Remember that we looked at the formula, which is just there on our poster. We looked at it in more detail here. We did some calculations. We looked at doing a calculation, a simple calculation. Then we looked at doing a ratio calculation where they said if you multiply the mass by this and you divide this by that, what's the effect on another variable? That's another way in which they can test your knowledge of this equation. And then they can talk about the differences in trajectories in r. If you increase the magnetic field strength, how does the radius change, etc. So they're different ways in which you can get tested, and of course they're on our poster. So this is the poster that you can get at thecrazyscientist.com. If your school does not subscribe to the video courses, then of course you can purchase these individually, hang them up in your study, test yourself frequently, etc. And so make sure that if you like what's in this video and you like the resources and everything, then like the video, give a subscribe, and of course come over and join us with the rest of the course here, and you will get lots of visual content. As you can see here, I've got my study cards, the formula sheets, the posters, constantly testing your brain cells. But not only that, you get worksheets, you get flashcards, and you get Kahoots, 10 Kahoots for every single video. And so that's a lot. That's hundreds of Kahoot questions that you can use anytime you want to study in a different way and compete against your friends and see if you can get a good leaderboard there. So that's it for this video. I'll see you in the next video where we continue to explore HSC Physics in terms of Module 6. See you then.